So welcome to another class of analysis of Boolean functions, and today we'll be discussing chapter 3 of Ryan O'Donnell's book, Analysis of Boolean Functions, which is the book we are following in this class. And so in this lecture, we'll be talking about the first part of chapter 3. Okay, so let's start with the definition. Okay, so we say that the spectrum of F is epsilon concentrated. Say in a set, say it's some family of subsets is a family of subsets of n. So say parts of the integers from 1 to n. If square, and if you take, is a family of subsets of n. Okay. So we have some subsets of n, and if we have this, and in here we have to normalize f by its whole norm. Okay, so that would mean that the spectrum of f is epsilon concentrated. It's supposed to be a complement in f, because it means that, well, the percentage of the L2 norm of the Fourier transform of f in the complement of this family is smaller than epsilon. Okay, so it means that it is concentrated in f. So another way of saying this, equivalent way of saying this is that the sum over the S over this family S squared divided by the sum over all the sets, which the L2 norm of f hat is greater or equal than 1 minus epsilon. Okay. So for instance, we say that the spectrum the spectrum of f is epsilon concentrated. On degree up to k if You take the sum over all the sets which have cardinality greater than k, of the square, of course, and this is less or equal than epsilon. It's L2 norm. Okay. So that means that, well, outside the set is very small, so it's epsilon concentrated in there. Okay. Yes. So another way of measuring that. So say that f is Boolean. So let me make an observation here. So say f is Boolean, which here is code word for saying that this is the Hamming cube, and then it's mapped to functions which only have 0 plus or minus 1 as values. That's what we mean by Boolean here. And then what you want to know is how can you measure this thing? So one way of measuring this thing. So this we can define as in O'Donnell's book he defined it like this. And then, but another way of looking at this thing is by the probabilistic point of view. So what is S of f here? So S of f is just a graph. So you have S prime here, S2 primes, and S3 primes. So these are just subsets of the integers from 1 to n, and you put an edge here, say pointing S prime to S3 primes if they are included in one another. Say, and the same thing here, and the same thing here. So in that way, you can build a graph which the vertices are the subsets from 1 to n, and the edges are given by inclusion, and you can put a weight which is exactly the square of the Fourier coefficient of f at that vertex. And if f is Boolean, we know that L2 norm is always 1. So this is a probability distribution. So this is like the spectral graph of f. And if f is Boolean, then we know that this is true. This is equal, it's like Poincaré is equal to L2 norm squared, but it only has plus or minus 1 as value. So this is 1, because we're using a probability measure here. And so this is indeed the probability distribution. And so what you can do is you can randomly select a set S in this graph. So this whole thing here, I should define what it is. S of f is this graph here. And then I randomly select one of these points with probability distribution given by the Fourier coefficients of f. And then I compute the probability that you take one set S with cardinality greater than k, that will be exactly this thing here. So you can see that and also in a probabilistic way. Okay. Another observation is, so this is just observation 1, observation 2, which it is, well, we know that the influence of f is defined as the sum of the influences of each coordinate, which which is exactly this. This is one computation we already did. But you can rewrite this as, say, k from 0 to n, k, where this, again, O'Donnell defines this as just the sum over all Fourier coefficients of size k, the square sum. Okay, and then, well, there is a very simple inequality. What you can do here is that if I summate over the k's which are greater than the influence over epsilon, well, you multiply and divide by this number. And so what you get is that this is, say, this is less than epsilon over I of f, sum over k, say greater than I of f, divided by epsilon, times k. Because k divided by that number is greater or equal than 1 in this summation, so we can do that. And therefore, I can even erase this. Let's say this is from 0 to n. And so what I get here is the influence again. So this all simplifies to epsilon. So this implies that f is epsilon concentrated up to degree IF over epsilon. So in a way, the influence of f is a measure, is one of these complexity measures, which we will talk more about later. But it is one of these measures that you can also translate in other things. For instance, you can translate the influence as a bound for the concentration of the spectrum. And here he's saying, well, if you have a good control on the influence of f, then you can have a control on the degree for which the Fourier coefficients of f are concentrated. Okay. Let's see if I have another remark. I do have another remark. Observation 2, no, 3, I guess. Yes, observation 3. Well, what is the probability of S being greater than K? So this is, again, trying to measure the concentration of the spectra. Well, I claim that this is less or equal than the noise stability, 1 over K plus 1 of F. So again, noise stability can be used as a tool to decide where the Fourier coefficients of F are concentrated. Let's see this. So what's noise stability? So let's show this. We'll recall that noise stability delta of F is defined as, well, the probability that F changes when you flip some of its variables. And here X is just uniformly distributed in the Hemingcube, and N is not exactly uniformly distributed in the Hemingcube, but say is delta distributed in the Hemingcube. And what I mean by this is that the N is made of of course, IID random variables also independent of the variable x, and such that probability of ni equals -1 equals delta, and the probability of ni equal 1 equals 1 minus delta. Okay. Again, this is the standard definition we always use. But then there is an identity we showed that this was also equal, and it's a simple computation, to 1 minus the inner product of f with the multiplication operator t. So recall that the multiplication operator t t of rho sends x to the s to rho raised moduli of s x to the s. Okay. So great. What am I doing here? So I want to derive an inequality. So let's try to do that. So then I have the 2 noise stability of, say, 1 over k plus 1 equals of f is what? Well, but this identity here is just a summation, is 1 minus the summation, and then we apply Plancherel, so that would mean that we would get exactly this. Yes, moduli of s squared, and then when we get yes, f squared, and then, well, there's this guy, 1 minus 2 delta to the power moduli of s. So I can even, well, now I'm going to use that f is Boolean. Yeah, I'm going to use that f is Boolean. So I should put here f Boolean. Okay, there are certain things that only are true when f is Boolean. There are certain things that can be extended to when f has real values or even complex values. So we have always to distinguish these things. Yes. So let's go back now. So if that is true, I can rewrite that as this. Okay. And then what, oh, and I have to prescribe then what delta is. So let's just, oh, okay, that was true, but now delta is this guy. Okay, so let me maybe erase this, call this delta. So say, let delta be 1 over k plus 1. So I know that delta, for instance, is between 0 and a half. K greater than equal than 1 here. Yeah, so k greater than equal than 1. Okay. So if that is true, then you have this, okay? Then what you can do is simply bound, say, so what I want is, if that is the case, then this number here is always positive. So I can just throw away some of these terms. So say I throw away everything bigger than k, a smaller, less or equal than k. And then I can rewrite what this is. This is just some I greater than k, and this is what? This is I 1 minus 2 minus, oh, sorry, 1 minus 2 delta to the moduli of S. W equals I of F. Oh, this is not S, this is I now. And this is, there is no I here. Okay. Then we're almost there. Now what you have to do is just simply, well, take the largest. So if I replace this by K, so replace this guy by K, I even get a lower bound. So then I get 1 minus 2 delta, well, K plus 1. This is supposed to be K plus 1, and then the sum. Okay, but what is this? Well, this we know what it is. This is just the probability moduli of S greater than K when S is distributed as the spectrograph of F. But what is K plus 1? So now I can replace everything here by K plus 1. So this will become K plus 1. K plus 1. And so what is this? This is also greater or equal than 1 minus epsilon minus 2. And then the same thing. And so we conclude what we wanted. We conclude that, we conclude the probability S of F is less or equal than 2, 1 over A minus 2, noise stability 1 over K plus 1 of F, which one we wanted. So noise stability is another way of controlling the concentration of the spectra of your function. Okay, so we should indeed show this inequality, and we had to use F Boolean. We had to use that F was Boolean. If F wasn't Boolean, then probably we had here the L2 norm anyway, and then we could do basically the same thing. And I bet we would get the same thing here on the right, except that, yeah, we'll probably get the same thing. Okay, but I will leave you that as an exercise. I don't know, maybe we don't get the same thing, maybe we do. Okay, observation 3. No, observation 3 is observation 4, actually. What happens with the majority function? So we studied the majority function already. And we want to know how the Fourier coefficients of the majority are concentrated. And the majority function can be weighted and can have a threshold. Okay. I will recall you what that is in a moment. But in any case, we do have this inequality, noise stability of 1 plus K plus 1 of the majority. And we computed that. That was less or equal, I think, by Paris inequality. That is just the square root of that guy. So this would be pi K plus 1. Yes. This is Paris. By Paris result. So then you know that the Fourier coefficients of the majority function, even when we have something weighted like that, they decay like this. That is, if you want to know how this is concentrated, say, I want to know if when this is less than, say, 0.01%, then I should take some K, like 1 over, it should be something like say 1%, then I should take k like 100. And then when you take square root of 100, you get something like 1 over 10 here, something like that. So, so bottom line, this is O of 1 over root k. So that's what you have to have in mind. And let me recall what the majority is. Majority function Wt of x is just sine, let me write here, is just sine of W1 x1 dot Wn xn minus t, say. Okay. And we saw the result of Paris that showed that this inequality was true. Okay. So, so now you know how the Fourier coefficients of the majority function is concentrated. Okay, let me define two things and let me prove a result. Definition. So f from H and to C is a M junta. See, of course, M less or equal to N. If it depends only on M variables. Okay. And then let me define the degree of f. I think I defined at some point. What's the degree? Degree of f is defined as what? Well, you expand that in monomials in a multilinear series, and you compute the degree of that polynomial. So we know that, so this is the degree of this sum by definition. So because we know that f can be expanded in such a way. So that is also the, say, the maxima of the size of a set such that f hat of s is not 0. Okay. Another equivalent way of defining the degree of such a function. And the theorem is the following. The theorem is, if you know that your function has a small degree, then you know that it cannot depend on many variables. So theorem. However, the bounding the theorem is in some way not that good, but anyway. I guess, yes, f is a degree of f 2 to the power degree of f minus 1 junta. Okay. So maybe I should drop this thing here. Just put it. Yeah, so if m here, so if a function depends on it's of n variables, then it depends on m variables for m greater than m, and well, it means that doesn't make any sense. So maybe I should keep it and then put the minimum here between n and this guy, because if whenever you go beyond n, it doesn't make sense. Okay, so it could be the case that this thing here is bigger than n, and this term is not saying anything. However, if your degree is very small, then it means that you live in a subcube of the Hamming cube. You don't live in the whole cube. Your function only like depends on the subcube. Okay, so let's prove that. I'm forgetting something. Okay, for the proof, I actually need a lemma first. So let me prove that lemma first. Lemma. If g is some function from the Hamming cube, the complex values anyway, and g is not 0 identically, then the probability that g is not 0, okay, is greater or equal than 2 minus the degree of g. Okay, let's prove that first. So let me do it by induction. So if n equals 1, checked, trivial. If from n to n plus 1, so what you do is you write g, you take the last variable, and you define this as these two functions. Okay. So in a way you can, so this implies that g of x1 up to xn plus 1 is actually equal to xn plus 1 divided by 2 h plus 1 minus xn plus 1 divided by 2 h minus. That's what it implies. And so then you can do what? What's the probability of g not being 0? Well, it's a half probability of g not being 0, conditioning to plus xn plus 1 being 1, plus also condition to xn plus 1 being minus 1. Okay, but if xn plus 1 is 1, that means this is the only term that survives. This is 0, and this guy is 1. So this is the same as the probability of h plus being not 0, plus a half probability of h minus not 0. Okay. So then you make the assumptions. Okay. So okay, but before we do that, let's see what is the expansion of h. So you had the expansion of f. Let me write here of g. Sorry. So g is that. So who is h plus or minus? Okay, so this is s contained in n plus 1. Well, so if the set does not contain n plus 1, there's nothing you can do, really. You just have this guy, s to the s. But if it does contain n plus 1, then you're putting that to be plus or minus 1. So that would be what? That would be just a subset of n that you add n plus 1 to it, and you do this. Okay, so that would imply that h plus or minus of x. So let me split this guy. So I could take subsets of n of, say, size. Well, you have to remember the degree of f, g. So let's say So say D is the degree of G. So S could be less or equal than D minus 1. And if that is the case, then I join these two guys. And if that's not the case, then I leave this guy because, so recall that the degree of G is D. So this guy can have at most size D. And there is one guy that has size D such that this is non-zero. And that guy can either show up here or can either show up there. Okay. However, these terms came from the guys that didn't have n plus 1. And these guys came from the guys, the sets S that do have n plus 1, because we had to remove it because we're setting n plus 1 to be either plus 1 or minus 1. So then you have what? Yeah, so these guys here, they can never, so all these guys here can never have degree D, D plus 1. Because, well, you indeed, sorry, D, because you indeed removed one guy from here. So this sum here is actually, I can even like do this. This is less or equal than D minus 1. And these guys, well, they can be less or equal than D, I don't know. And why these guys are less or equal than D minus 1? Because you remove the xn plus 1 variable from them. Okay, so the degree of G is at most D. So that's what you have. So then you group those which have degree less, and then you leave those which have degree exactly D out. So you can write like that. Okay. So now let's make some assumptions, and maybe I can explain only in words. Suppose that both are non-zero. Well, if both of non-zero, let me put in cases. If H plus and H minus are both not zero, then by induction, the probability of H plus or minus not being zero is greater or equal than 2 minus the degree of H plus or minus. So what's the degree of H plus or minus? Well, at most T, so it would be D. So therefore, the probability of G not zero is greater or equal also to the minus D, as we wanted to show, because we have these 2 halves here. If that's not the case, this is case 1, if say H plus is identically 0, then H minus cannot be identically 0. Because let's see, if H plus was 0, that means that this is 0, this whole thing here is identically 0 when I put plus here. Well, these guys only live with S less or equal than D minus 1. So if that is 0, this part here has to be identically 0, meaning these coefficients here have to be identically 0. Okay, so this part is gone. But then then you look at those guys here, if H minus was identically 0, then you could say add them both, H plus or H minus, and only this bit would survive. So these guys also will be identically 0. And if you do the difference also, I mean, these guys would be identically 0. So everything would be 0. Of course, they cannot be both identically 0, otherwise G itself would be identically 0. That's another way of saying it. Okay, but it's more than that. This is kind of obvious, but what I just said says that the degree of H minus is actually less or equal than D minus 1, because if plus is 0, this part has to be 0. And then you only have things with degree less or equal than d minus 1. Okay? And then, of course, it has to be non-zero h minus. So then this is just equal to the probability of h minus being not 0. But by induction, this is greater or equal than a half, 2 to the minus 1 minus d, which is 2 to the minus d. And so we close the induction case. Okay. So it's just a simple trick. So now we can go back to the proof of the result. So let's prove the theorem. So the proof of the theorem is saying that this guy is always adjunta. So let's prove that. Well, let me give a name to that theorem, say Theorem One. The proof of Theorem One. And how can we prove that? So first of all, we do know that say, let's see what I want to do first. Okay. So what's the influence of a variable I? Well, we do know that the probability of the derivative in the direction I being not 0. Okay. This is again one of these identities we showed. But then what we just showed, so this guy is just another Boolean function. So when you do differentiation, you always decrease one degree. So if that guy has, say, degree of f is d, this guy has degree less or equal than d minus 1. Okay, so by what we showed is that this is greater, that this is 0 or greater or equal than 2 to 1 minus d. Okay, by the lemma we just showed. And so therefore, if you compute the influence, which is just the sum of these guys, this will be greater or equal than 2 to the minus 1 minus d times the cardinality of the i's, such that the influence of I, of the variable I of f, is non-zero. Okay, but f depends on xi if and only if the influence of I is different than 0. Because of this identity, what is the derivative here? Recall that the derivative here at some point x is just f of x when you put xi equals 1 minus f of x when you put xi equals minus 1 and divide by 2. Okay. And so if this is identically 0, okay, if this is identically 0, then that means that f does not depend on the variable x, I, and therefore the influence is 0. However, by the Fourier also has a Fourier expression, which is this one, when I belongs to S. So I belongs to S, like does not belong to S. I always forget. I think it's I. Let's see. By that is I think it's I belonging to S. Yes. Then so maintenance. Yes, it's exactly that. This is always greater or equal than 0. Okay, so the influence is always greater or equal than 0. It's exactly 0 when f doesn't depend on xi. So so this is actually counting, this is just 2 to 1 minus d, the number of variables that f depends. Okay, but on the other hand, the influence, which is this sum, okay, subsets. Well, of course, that I can only summate when this is less or equal than the degree of f, because all the other guys are 0. So you can just bound this by d, the sum of everything. Okay, and I'm assuming that f is Boolean here. So did I assume that f is Boolean? So I have to assume f is Boolean. There are things that if you don't assume that f is Boolean, then there is just like an L2 norm multiplying both sides of the equation. There are the things that you can't really deduce without assuming f is Boolean. But in any case, this is just d, because whenever f is Boolean, the L2 norm is 1. So then you know this, and then you conclude that the number of variables that f depends on is less or equal than d divided by that term, so 1 minus, d minus 1. And that's the end of the result. So this is so it depends only on these many variables. So I think if you have something like n equals 1,000, say, and I think 7 is the largest. If you put 7 here, 2 times 6, I think you get something. I can do this computation now. I think you get like, so one example here, small example. So say n equals 1,000, and you put d equals 7. So then you get this thing is 448. So function. So if you have a Boolean cube, a Hamming cube of size 1,000, dimension 1,000, and you have a function that depends only, Boolean function depends only on that has degree 7 at most, then it actually depends on less than half of the variables. But if it has degree 8, then the number, I think, is like, then if d is 8, then this guy is this guy, which is bigger than 1,000. So then the bound doesn't tell you anything. Okay, so this is bad. So yes, this is just one, say, numerical example. And just to finish, let me discuss a little bit about decision trees, and we can finish this class. Okay, so what is a decision tree? So suppose I give f a Boolean function. Okay, and let's imagine f here being, for instance, the sort function. Which is 1, say, which is, so yeah, so one way is to identify, so let me, for now, just identify the Boolean cube with 0 and 1, and this guy is just with 0 and 1. So the usual identification is -1 is identified with 1, and 1 is identified with 0. Yes, and the map here is always x2 1 minus x over 2. Okay. This is nice because this identification takes, so additive properties here are mapped to multiplicative properties there. So that's usually why this is done. Okay. So what's the sort function? The sort function will be what? Say 1 if the variables are in order or in reverse order, and 0 otherwise. Okay. So so this will be sort n. So let's try to compute a decision tree for sort n. So first of all, there is not a unique decision tree. So let me just try to do an example here, and then we'll see exactly what it is. For sort 3, say. So I could start with, so just 3 variables. It could start with x1, and I want to know if the variables are ordered or not, say. So if x1 is 1, then I query x2. Well, if x2 is 0, then, well, it could be the case that the direction is reversed. It's like x3, x2, x1. So I have to ask if x3 is 0. If it is, then I give the answer 1. If it's not, if it's 1, then the answer should be 0. Well, if x2 is 1, then it doesn't matter what x3 is, because if x3 is 1, then you have a certain order, and if f3 is 0, then you have another order. So whatever it is 1. So I don't need to query x3 in here. Then, well, query x1, and then I give 0. Then what you can do is you can query x3. Well, if it is 1, then no matter what x2 is, this thing always has an order, and a reversed order will work. So this would be 1 anyway. If x3 is 0, so then there is only one possibility. x2 has to be 0. And if it is, then the answer is 1. And if it's not, then the answer is 0. So this is a decision tree for computing the function sort 3. Okay, so the nodes in this tree are the variables, and the edges connecting are always labeled, always have a label, either 0 or 1, meaning the possibility of the variable at that point being 0 or 1. Okay, so you see often, so the general structure, you have some xn variable, and you have a possible variable 1 or 0, and then you query some xm here. It doesn't need to be in order. As you saw, I query x1 here, and then I query x3. I could start with something else. I could start with xn or whatever. But the bottom line is that this is more or less the structure. This is what you will see in the structure of a tree. Okay. So that's the decision tree. And we can have more than one decision tree. For instance, I could, for instance, do something naive and replace that. And replace that 1 here, and I could like query x3. I didn't need to query x3 because I already know the result, but I could, if I wish, and put 2 more other guys here, and then both would have to be 1. So that tree could be reduced, say. So yes, so you can always like reduce the tree whenever you have some node here that whatever all the leaves have the same value. You can just reduce it. So you can always assume that this given tree is reduced, but there are other trees because I could instead move to x2 here, say instead of x3. And so there are other trees, although every tree can be like reduced. Yes, and so we have another definition here. And again, another one of these complexity measures, which is the decision tree complexity measure of F, which is the minimum depth. It's the minimum among all the depths of T, where T is a decision tree, for F. So what is depth? Well, we can guess. Well, what is the depth? 1, 2, 3. Okay, so the depth of this tree is 3. So you can actually show that the decision tree is sort 3 is 3. Okay, decision 3 measure of complexity of sort 3 is 3. And so you take all these trees, and the one who has the smallest depth is the complexity. And that is, well, that's the optimal tree you can actually write to compute your function. Okay, so let me give some observations here. Okay, so first of all, every x in, say, the Boolean cube, you could do the same with the Boolean cube instead of F2. So let's keep with F2, for instance, follows a unique path. So let me go back to this. It doesn't matter. So suppose I give you a decision tree, T. And you look and I say, well, every x in the Boolean cube, in the Hamming cube, follows exactly one path because, well, if my x is decided, it's like 1, 0, 0, for instance, then I have to go this path and this guy and this guy. Or if it's 1, 1, 1, say, then it's this guy and this guy. So every x follows exactly one path. Okay, and so you could say define CP as a subset of Hn as CP to be the x's in Hn that follow path P. Okay, so you select a path, say this one, and you say, well, what x's follow exactly this path? Well, in this case, only one, but you could select this path, for instance. In this case, you can say, oh, there's actually 2 guys, because I can put 1, 1, 0 or 1, 1, 1, because x3 doesn't matter in this path. Okay. And so, but then you see that that CP is a subcube of Hn. But we just saw here that the last variable here doesn't matter, so I could put any of x3, and that's a subcube. And in general, that's what happens, because CP will be exactly of the form the x's such that some subset say there is some xi1 and xi2, I don't know, m equals to some things. Because that will exactly be a path, because a path is only like querying some variables. It doesn't need to be in order, it could be any order. So those that appear in the path are prefixed, but the others, the ones that don't appear, they don't appear, so they can be anything. So the cube will be certainly be something like that, the CP, which is another cube. So in that way, and also you see that f of x is always equal to f of y if x and y belong to the same cube. Okay, because again, the decision 3, the answer is in one path is predefined. So in this way, you can say that your function f of x is actually the sum of this common value, let's call it f of p, and the indicator of this guy, p, where p is a path of t. Okay. And so you can write your function in that way. So that is some sort of a complete reduction of your function, because you know exactly what the values of f of p have to be in those cubes, and that's the only thing you need to know. So computing the decision 3 for a function is actually something very useful computationally to actually compute your function. But from here, you get a very nice observation. So what's the degree of this function? Well, we know what it is. This has to be this guy if C has this form. Because it's whenever I have exactly these numbers, all these guys will be 1. And when I have any disparity here, I will have this guy to be 0. So that's the indicator of this guy. And so I want to know what's the degree of this thing. Well, the degree of that thing is exactly m. But what is m? Well, m here is the depth, the length of the path. And therefore, we conclude that this guy is less or equal than, this is the length of the path, which is definitely less or equal than the depth of the tree, because it's the maximum among all those lengths. Okay. And so therefore you conclude that the degree of f, which is less or equal than the maxima of the degree of all these functions, is less or equal than the depth of t. And so if I take the infimum among all of these numbers, I get the decision 3 complexity of f. So nice. This is a complexity measure. This is another complexity measure, and you have this inequality. Okay. And then we will see later on that when we define other complexity measures, that in most of the cases, they're always linearly related or even polynomially related. Like there could be something like a cube here or something else. Okay, so you see that, and there are a bunch of very interesting and hard questions about relations of complexity measures that we will see. And this is just one small instance of that. And I think I will finish here, and we will see each other in our next lecture. Okay, bye-bye.